Hi there, it's Paul, ready to teach you about uncountability. You know now how to prove that an infinite set is countable. You have to establish a one-to-one correspondence, a bijection, between it and the natural numbers. In order to show that a set is uncountable, you have to show that no such bijection can exist. You might think that showing that something is impossible would be difficult to do, but in fact it's not. What we're going to do is to assume that the real numbers between 0 and 1 can be enumerated, put into a list, assigned serial numbers, and then we will show that that assumption leads to a contradiction. This is a famous proof from the late 19th century due to Georg Cantor. It was quite controversial at the time, but since then it's become a staple of mathematics. So I'll set up the screen and I will generate 100 random digits. That is, I'm sampling 100 times from the set 0 through 9 so that I can generate the beginning at least of 10 different decimal expansions of real numbers. Don't worry about the details of the plotting function. That just puts things nicely on the screen. Now let's suppose that someone has told us that they have found a way of listing all the real numbers between 0 and 1, assigning them serial numbers. And I say, what does your list look like? And they say, well, here's just the first 10 things on it. I'll list the first 10 numbers, and the ... at the end means I'm only going to show you a certain number of decimal places, but you can have as many as you like. So each of these numbers, in principle at least, is an infinite decimal and can be regarded as a real number. Now we plot the digits. We show the first 10 digits of each of those numbers. And you might have wondered, why did I show some of these in red? Well, that's the great trick of the proof. I am now going to construct a number that cannot possibly be on this list. How am I going to do it? Well, I'll call it x, and I will look at the top number. The top number has a 3 in the first decimal place after the decimal point. If I subtract 3 from 9, I get 6, which is different from 3. So I'm going to start my number x off by putting a 6 in the first position after the decimal place. To get the second decimal digit of my number x, I will look at the second digit in number 2, subtract that 6 from 9, and get a 3. And now you get the idea. 9 minus 5 is 4, 9 minus 9 is 0, 9 minus 1 is 8. Notice that there's no way that 9 minus a digit can ever be equal to that digit. And so I have constructed the first 10 digits of a number that is guaranteed to disagree with each of the 10 digits on the list. Now this same construction would work in principle for an infinite list. So what have I shown? I've shown that if you give me a list that purports to include all the real numbers between 0 and 1, you are a liar, because I can, by this procedure, construct a number that cannot possibly be on your list. If you say, oh, that's the 8th number on my list, I know it, I say, no it isn't, because my number differs in the 8th decimal digit from your number. Subtracting from 9 is my favorite way of generating this number, but there are a large number of ways of doing it. You might, for example, be a fan of St. John the Divine and want to do this in a rather more apocalyptic way. So let's construct the number y. What I'm going to do now is look at that 3, the first digit in the first number, and ask, is it a 6 or is it not a 6? If it is a 6, I would turn it into 1. Since it's not a 6, I will turn it into a 6. Look at the next red digit, the second digit of the second number. That is a 6, so I write a 1. I continue, and how apocalyptic, I have generated the number of the beast, 666. Actually, this is a rather large beast. So we've got 66666, but you get the idea. This is another example of a number that cannot possibly be on the list. When you do this proof, you might want to invent your own ingenious way of changing all the digits on the diagonal. Any method of doing that is as good as any other. Now I'm going to show you something that looks quite different, but that will in fact, on reflection, turn out to be exactly the same argument. If I start with a set, capital S, whether finite or infinite, I can construct its so-called power set, which is the collection of all subsets of that set. The notation 2 to the s is appropriate because in the finite case, if a set has n elements, there are 2 to the nth possible subsets of it, because there are two choices for either including or excluding each element of the set. The next is a bit of our cleverness, starting with a vector that goes from 1 through 9. What I can do is generate another vector by taking 9 random samples from 0 and 1, and then asking when is that greater than 0, i.e. when is it 1, and that selects a random subset. In this case I get 1, 5, 7, 8, but every time I do this I'm going to get, in general, a different random subset. So now I can define a function whose domain is the set S, 1 through 9 in our example, and whose codomain is the collection of subsets of 1 through 9, the power set of S. Let's see what that might look like. You can see that f of 1 turned out to be the set containing 1, 2, and 5. F of 2 turned out to be the set containing 4 and 7, and so on. Now comes the clever step. I'm going to make a new vector x that can't possibly occur as one of the 9 function values. Since it's rather tricky to get R to do this, I'm just going to do it by hand. So the first question I ask is the digit 1 included in f of 1? Well, f of 1 is the set 1, 2, 5. That's got 1 in it, so I don't want 1 in the set x. But 2 is not included in f of 2, which is just the set containing 4 and 7. So I will include 2. 3 is in f of 3, so I don't want 3. But 4 is not in f of 4. 5 is in f of 5, but 6 is not in f of 6. 7 is in f of 7. 8 is in f of 8. And 9 is in f of 9. So I've now constructed a 3-element set, x, and let me display it under the others. It contains 2, 4, 6. And that can't possibly be on the list. Why can't it possibly be on the list? Because, you ask yourself, could it be f of 1? No, it couldn't be f of 1 because 1 is not in the set x, and therefore f of 1 does have to contain 1. So f of 1 couldn't be 2, 4, 6. What about 2? Well, 2 is in f, which means that f of 2 has to be a set that doesn't contain 2. But x is a set that does contain 2. And to summarize the argument here, there's no way that this set x can be the same as any value f of n, because x, by design, disagrees with f of n about whether or not n is a member of that set. Now you might say, this is silly. You've got 9 digits. There are 2 to the 9th possible subsets. You're only using 9 of them. 9 is less than 2 to the 9th, so there's no way this function could be surjective. And you're absolutely right. In the finite case, this argument is totally unnecessary. There's a much simpler one. But this argument still works in the case where S is an infinite set. And in that case, what it tells us is that there can be no correspondence between the natural numbers and the collection of subsets of the natural numbers. Why? Because I can construct something that is not in the image of F. That means that F cannot be surjective. A one-to-one correspondence is bijective, must be injective and surjective, and not surjective means not bijective, means no one-to-one correspondence, and therefore the collection of all subsets of S, while definitely an infinite set, cannot be a countably infinite set. It must be uncountably infinite. If you think about this carefully, I'll leave it to you to do this on your own, you realize you could replace 1, 2, 5 with something like true, true, false, false, true, and a bunch of falses, and use the same diagonal construction that Cantor used in order to establish this argument. So it's really the same argument expressed in a different way. You might on your own want to rerun this script starting at the line where F is defined. You'll get a different collection of sets on the right. You'll have to rebuild the vector x, and that's a good way to practice this argument on your own.